Hello, my name is Ben, and this is Math with Ben. Today we will be starting a new series on mystical math words, starting with vector spaces. I believe that math is this big, scary subject to most people, which I don't think it should be, because we have these mystical math words, as I like to call them, and definitions and theorems that to the average person, sound ridiculous and absurd, like an isomorphism is a homomorphism that is a bijection. Um, what? Right, like exactly. So today we'll be starting with vector spaces. I'll be explaining what a vector is, what a vector space is, the 10 axioms of vector spaces, what a basis is, and then an example to think about. And that will be that. And then I think next time, like I just said, I'll be talking about isomorphisms and homomorphisms and what they are and what they do and how they can relate to vector spaces. I want to connect each video to the previous one to kind of build up on math, which means vector spaces is kind of a weird place to start, which I agree with, but it was the first thing that came to mind, so that's what I will be doing. So before we can talk about what a vector space is, let's talk about what a vector is. I'm sure a lot of you know. There's not many people watching math YouTube, I would say, that don't know what a vector is, but that is no problem if you don't. A vector can be viewed in one of two ways usually. There's a geometric interpretation, which is usually used in physics, which is an arrow from the origin that points to some place in space. And then there's an abstract interpretation that's usually used in pure mathematics and data science and computer science, where it's an ordered tuple of numbers defined by components. So for the core geometric concept, a vector is defined entirely by its magnitude and direction. Like I was saying, it points to some position in space, so it's represented by length, which is the magnitude of the vector, which is usually represented by the Pythagorean theorem. So you can do the square root of all the components squared added together. And then the direction is given by a linear combination of unit vectors. So a unit vector is a vector in space. So let's say we're looking at a two-dimensional plane. There are two unit vectors for this two-dimensional plane. This is something I'll talk about later. And one of them is I hat and one of them is j hat. So I hat points along the x-axis and has magnitude 1, and same with j hat, except it points in the y direction. So these are two unit vectors, and any vector in the two-dimensional plane can be represented as a linear combination of those two unit vectors. So as you can see there, example, the vector v is 3 hat plus 4 hat, so it's 3 units in the x direction and 4 units in the y direction. And then the more abstract view, we can define a vector as a list of numbers in a way. It's different than a set, but it's still kind of a list of numbers. It's represented by either a column or a row of numbers enclosed in brackets, and as you can see, this vector here is 3, 1, where this 3, again, it's the same exact vector as the one before, except the 4 turned into a 1. It's just a different way of looking at it, and this one is more useful for what we will be talking about. So let's jump right into what a vector space is. A vector space is a set of vectors with numbers called scalars, which are non-vector numbers, that satisfy 10 axioms, but the most important of which are closure operations. Now, these aren't actually part of the 10 axioms, but they are. One of them is scalar multiplication is, vector addition is not, but they are taken to be axioms of vector spaces. They're just not the main 10. So the closure operations for any vector space we'll call S, the following two rules must hold true. So the first one is vector addition. If any two vectors v and u are in the vector space S, then v plus u is also in the vector space S. And for scalar multiplication, for any scalar in some generic field f, which is usually the real numbers or complex numbers, This scalar r in F multiplied by a vector, which is in S, is also in S. So it's closed under vector addition and scalar multiplication. So why does that matter? So as I said, this matters because of something called closure. The rules of vector addition and scalar multiplication that mean no matter how you stretch or bend a vector, the result will always be an element of the vector space you are looking at. Now let's look at the 10 axioms of vector spaces, starting with rules of vector addition. So for any vectors v, u, and w in S, which is our vector space, the following 5 vector addition axioms must hold true. 1. Commutativity. So v plus u equals u plus v. Associativity. V plus u plus w equals v plus u plus w. Additive identity. There exists a zero vector in S such that v plus 0 is v. Additive inverse. For all v in S, there exists a negative v in S such that v plus negative v is the zero vector. And closure of vector addition we already talked about. So what this means in English is that 1, the order, so for commutativity, the order of which you add two vectors does not matter. 2, for associativity, it does not matter how you add 3 or more vectors together. 3, there is a zero vector, which is an additive identity, as in it changes nothing when you add it to any other vector. And 4, there is a negative vector for each vector in S such that when you add them, the resulting vector is the zero vector. Now for scalar multiplication, for any vectors v, u, w in S and scalars a, b in a field F, there is closure, which means a times v is in S. 7, distributivity over vector addition. Any scalar a times two added vectors is au plus aw. Distributivity over scalar addition. So a plus b, which are two scalars, times v equals av plus bv. 9, there is a multiplicative identity 1 such that 1 times v is v. 10, associativity property of scalars, ab times v is equal to a times bv. So what this means in English is that 7, multiplication distributes over vector addition. 8, multiplication distributes over scalar addition. 9, multiplying any vector by 1 changes nothing. And 10, scalar multiplication is associative. So let's talk about a basis. A basis is one of the most important concepts when looking at vector spaces because you can use a basis to describe a whole vector space with just a few vectors. So like I said, a linear combination of two vectors is two vectors added together which are each multiplied by an independent scalar. So for example, a times the vector v plus b times the vector u is a linear combination of v and u. So an entire vector space can actually be expressed as a linear combination of its basis vectors. So a basis is the minimal set of vectors that acts like a coordinate system for a vector space. For a set of vectors b equal to the set v1, v2, all the way to vn, in S, it must follow linear dependence. So no vector in B can be written as a linear combination of other vectors in the set. 2, it spans the entire space, which means every vector in the space S must be able to be written as a linear combination of vectors in B. So what this means in English is that there's no redundancy. Every vector in your basis provides a unique direction. If you remove even one vector, you lose access to part of your space. What this usually means is that each vector is orthogonal or perpendicular to one another. As I go back to the example earlier in the two-dimensional space, I hat and j hat are 90 degrees away from each other. They're orthogonal to each other. And any vector in the entire plane, two-dimensional plane, which is also known as R2, can be written as a linear combination of I hat and j hat. The other meaning is that in total coverage, the vectors act like a basic navigation commands, up, down, left, and right. By scaling and adding them, you can travel to any destination in the space. Like I was just saying, in R2, if you take a linear combination of I hat and j hat, you can reach any vector that's in the entirety of R2. So now let's think about an example, and then I will do some problems on my notepad to show you all how you can prove something's a vector space, how you can disprove something's a vector space, and then we'll take a look at a couple more examples that you might encounter in a linear algebra class. So our first example that we think about in the slideshow is the set of polynomials of any degree. So the set of all algebraic polynomials of degree n or less forms a valid vector space. So vectors as functions, we can think of any degree polynomial as a vector in this vector space. Vector addition, adding two polynomials yields a new polynomial of the same or lower degree. So if we have a vector space of polynomials of degree 3, or in this case degree 2, I suppose, if we add any two polynomials that are of degree 2 or less, any resulting polynomial will also be a polynomial in the vector space because it will always have degree 2 or less. Scalar multiplication. Multiplying by a polynomial by a scalar simply scales the coefficients. So there is no scalar you can multiply that would change the degree of any polynomial. So therefore, a polynomial of degree n will always work as a vector space. So now let me jump into my iPad and I will show you guys some math that we could do with vector spaces, how you can prove something's a vector space and whatnot. Alright, so let's jump right into looking at vector spaces. So the first example we'll do is R2, something I've already talked about. So we have this two-dimensional plane where this is the x-axis and this is y-axis. Now you should all, if you've taken a couple math classes in your life, you should be very familiar with this. This is just, the real number line crossed with the real number line as two axes, the x and y axis. Functions are usually written f of x equals y, where x is an independent variable and y is a dependent variable. So let's look at what a unit vector looks like on the the R2. So we have this vector and this vector, where this one is I hat and this one is j hat. Now we have the vector space R2. Let's write it out. Like I said, we actually have, or know from my earlier definition, that a vector space is a set of vectors with scalars to multiply them to get any linear combination that spans the whole space. So we'll write this as, if we take, for example, the scalars I already mentioned in the field of real numbers or complex numbers, if you want to think about it, but because this is R2, we'll be taking them as real numbers, a and b. A times I hat plus b times j hat, such that a, b are in the real numbers. Now this is a vector space. This is exactly what a vector space looks like, written in set notation. And that's it. So if we want to take the vector v, if we want to find v, let's say it's this vector. To me, that looks like, I'd say 3 halves I hat plus 2 j hat. Now this is a vector that's written as a linear combination. I'll write that down. Linear combination of two vectors I hat and j hat, which are the basis vectors. So if we want to know what the basis is, basis of R2 is what? Well, I already said that a basis is two vectors that can be written as a linear combination to span the whole space. So I've already showed you what the unit vectors are. They're I hat and j hat. So the basis, we'll call it b of R2, is equal to the set Oh, that's bad. I hat and j hat. Oh, God. Which is also equal, if we want to use the more abstract notation that I wrote earlier, 1, 0, 0, 1. This is 1 unit in x direction. This is 1 unit in y direction. Oops. And we can see how this spans the whole space, right? If you take any linear combination of I hat or j hat, you're bound to get a resulting vector that's in R2. That's the one example I'll do for you today. Next time we'll be talking about isomorphisms and homomorphisms, and I hope you have a great rest of your day.